So, really, we have 5 days and then finals. So really, we have 5 days. Because if you probably want to take in pre-calculus doesn't have a final schedule during finals week. We already took our final. We're good to go. We're on there. We're done with that. So, last week, Wednesday, we took a test, and neither Schmeling nor I got to those this weekend. So we'll get to those today and tomorrow, or we'll have those hopefully in the grade book by tomorrow. Okay. How it's going to go? He's going to correct everybody's calculator portion. I'm going to correct everybody's math. We kind of like doing that with the final, so keep that up. Probably have that next year, because then everything's consistent. So. Okay. So this week we're going to talk AROCs and IROCs. We'll talk a little bit about that. We'll talk a lot about that today. We're going to actually get to IROCs today too. So rates of change. Okay? You've seen a lot of them. You probably saw a bunch of them today when you came to school. Right? If you drove yourself into school today, you for sure saw a rate of change. Okay? Your speed, your speedometer. Okay? That's a rate of change. If you're like me, you have your fuel economy somewhere on your dashboard. Okay? That's a rate of change. Okay? Miles per gallon, MPG. That's a rate of change. Okay? Meters per second, feet per second, miles per hour, parts per million, megabytes per second. Anybody know what GPF is? I wouldn't expect you guys. This is more of an adult thing, especially when you're remodeling your bathroom. Gallons per flush. Yep, gallons per flush. Yep. GPF is gallons per flush. Okay. Right. Higher gallon per flush, means obviously more water going through your toilet every time you flush. Yep. Yep. So as an average, we call those average rates of change. Okay. In order to have an average, you got to have at least 2 data points. Okay. So an average rate of change would be the rate of change between 2 set times or 2 set conditions. It's not always going to be time, is what it's always going to be. It could be, like, we'll use a farm one, okay? Seed per hopper, okay? Not a time, but how many seeds are sitting in one particular hopper, okay? So that an average rate of change, you need to have at least 2 of them. If we're looking specifically at a point in time, then that's going to be the IROC, the instantaneous rate of change. Okay? So AROC is average rate of change. IROC is instantaneous rate of change. When we get to the end of class today, and I hand out your first homework sheet, yes, we even have homework during this unit too. It's going to be very crucial for you to read what that particular question is asking. To look for that A or for that I, because they are calculated in 2 very different ways. Okay? So let's start in here with this function. F of x equals x squared minus 6x plus 5. We want to graph that function first, okay? And then we want to find the average rate of change graphically and algebraically. Okay? So let's graph this function. How are we going to graph f of x equals x squared minus 6x plus 5? What shape is it first? That's going to help us. It's going to be a parabola. Is it going to be a bowl parabola or a camel hump parabola? Bowl, because it's got a positive a value, so it's going to open up. Yep. Okay. So that means we need to find that low point of that vertex, right? Okay. How are we going to do that? We could, okay. So we'd have to complete the square then, right? Okay, do we want to do that? Well, we can. I mean, I love that you suggested it. Do we want to? Okay, what's an easier way? We could factor it. If I factor it, first off, is it factorable? Yep,
Yeah.
okay. And then what's the factors going to give me? It's going to give me the zeros, right? The solutions, the x-intercepts, right? Okay. So if I factor this, what does it factor to be? So that would tell me that I've got a 0 at positive 1 and positive 5. Yes? Okay. So halfway between those two, or the average of those two, is going to be what? What?
3.
3, okay? Right? So that means my vertex is going to be at f of 3. Yes? Okay. So 3 squared is 9. Minus 18 is negative 9. Plus 5 is negative 4. Do you agree with that? Okay. So that means I'm here. Okay. Would I be here and here also? Yes? Yeah, because it follows the 1, 4, 9 pattern, because my A value is 1. So then I would also be here and here. And then I think I'm off the graph, because I think the next one's actually at 12. Okay. So we can draw in our parabola. Okay. Now it says graphically find the average rate of change between x values of 2. So my x value of 2 would be at negative 3. And, excuse me, 6. My value of my function at 6 would be 5. How can I graphically find the average rate of change between those two big points? Yes, it is that simple. It's the slope. Yep, exactly. It is the slope between them. Okay. So my AROC is the slope on the graph. Okay. So one way to do that is you could go rise over run, is one way of saying it. You could go, because we have the 2 points that it goes through, we could go y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Whichever any of those ways that you do to do that voodoo that you do so well. Okay, however you find slope, that's you. Okay, all right. So this is going to be then 5 minus a negative 3 all over 6 minus 2, which is going to be 8 over 4, which is going to be positive 2. Does that make sense that we have a positive rate of change between those two? Yeah. Because it is going up and to the right. But follow-up question. The average rate of change for this function, will it always be 2? Okay. Yep. I don't think no, because there's no cars in the parking lot. I don't know. Yeah. I don't know.
There's lots of cornballs.
Yeah.
It is the freshman. Oh, that's.
But they're not. I don't see anybody. Like me too. I'm like, wait a second. Track meet sounds. And by the way, this is a riveting video for anybody that's watching right now. I want you to know that. Yeah. Heard. They were screaming outside, which you probably heard on the video. All right, so we got two. Yep. Okay. Average rate of change now algebraically. Okay. So another way of saying AROC is if you have an interval from A to B. Okay? So that to find the average rate of change, you need to have an interval. Okay? You need to have an input interval. I don't want to say X because more than likely it's going to be. Okay? You have to have some kind of an input interval. And then that is going to be, then you're going to take the value of the function at your right end. You're going to subtract off the value of the function at your left end. And you're going to subtract by how many it is to get that interval. Okay? Which is basically, if you think about it, it's basically the slope formula. The value of the function is the y values, and then you have the x values to go along. Okay? So we've actually already done this function. We've already done this calculation because f of b is 5. F of a is -3. B is 6. A is 12. So here is a parametric function. Okay. Position of a golf ball hit off a 3-inch tee, sticking 2 inches out of the ground, is given by the parametric equation of that. Okay. What unit are we dealing with? Just so we know. I will agree that we are dealing with seconds because it's a parametric function. T is going to be in seconds. I agree with that. But I do not agree that we are in inches. The reason that I know we're not in inches is because it's not 2 down here at the end. What? Anybody know what unit are feet? We're in feet. Yep, we're in feet. Because if it was 2 inches, 1/6 would be like 2 over 12. So that means 1 foot is 12 inches. So we're in feet and we're in seconds. Yeah? Okay? So question number 1 says, what is the vertical position of the ball 0.5 seconds into the hit? Vertical position of the ball. Okay, first off, freshmen don't really scream like that.
I believe the freshmen, they're up.
Are they up? Are they
I
up?
see people up there.
Yeah, but that's 4 people, and they're playing cornhole.
There's probably like more than
All that way? Okay. Okay. Yeah, they literally sound like middle school volleyball. Yes. Yeah. Okay. So how am I going to figure out the vertical position? Oops, type one. Plug what in, where, and where? I'm going to plug in 0.5 for t in the y of t equation, okay? Because y of t is going to give me my vertical position, and that's all I want, right? Okay, right? So we're going to go y of 0.5 is going to equal negative 16 times 0.5 squared plus 110 sine of 60 degrees times okay. A calculating device would be very much handy. I get my position is 43.798 feet off the ground. Do we concur? Forgot the 1/6. Agree? Okay. Vertical position of the ball 3 seconds into the hit. So now what are we going to do? Plug in 3 for t in y. Same thing. Find it. Anybody? Question number 3 says, what is or what was the vertical displacement of the ball between 0.5 and 3 seconds? What does vertical displacement mean? Actually, I didn't shrink it up. Just displacement. Change? Okay. So how am I going to figure out the vertical change in the ball in that time? Subtract them, right? Yeah. Agree with 98.157 feet. Yeah. Okay. Now, it's asking us to calculate the vertical velocity of that ball over that interval. So what would I do now? Divide which one by 2.5? By vertical, by change in vertical distance divided by how long it took me to make that. And then my label would change to feet per second, correct? Which would also be, we could also call that the average rate of change on that interval. Yes? The AROC? Because that's basically what we did. We found the position at 3 seconds, we subtracted off the position at 0.5 seconds, and we divided that by the time. Yeah? All right? Love it. So again, the difference quotient is that AROC formula. Okay? So it's my average rate of change on the interval from A to B of, so in this case it would be F of B minus F of A all over B minus A. That would, we call that the difference quotient or the DQ. When you get to calculus, side note, I forgot to say welcome to your first day of calculus. That's what this is. When you get to actual calculus next year with J. Crew, f of t, that function, okay, it's going to be defined for you as something. And then it might be a relatively easy one. It might be a relatively complicated one. Okay? But that function could represent various quantities, such as oil spilling, the amount of sand piling up in the shape of a cone at the end of a conveyor belt, etc. Okay? What the difference quotient will find is the rate at which that quantity is changing. And that quantity can be whatever it is that you want it to be. Okay? Or I shouldn't say what you want it to be, whatever it is you're trying to find. Okay? So if it's like cubic yards of sand per hour, or gallons per minute of oil spilling, etc. It's that. And then you can also adjust it to, like if it was an oil spill, let's say it's an oil spill, the area of the spill, could be expanded, or things of that nature. So, okay, let's get into it here. So let d of t equal 3t squared represent the distance an object is away in meters from its starting point after t seconds. Find the average rate of change over the interval 3 to 6 seconds. So that would be d of 6 minus d of 3 all over 6 minus 3. Do we concur with that assessment? Okay. So d of, oops, oops, erase. Be 3 times 6 squared. 6 squared is 36 times 3 is 108. d of 3 is going to be 3 times 3 squared. 3 times 3 squared is 9 times 3, which is 27. 108 minus 27 is 81. 6 minus 3 is 3. So my average rate of change here is 27 meters per second. Yes? Yeah. But 3 seconds is a pretty big gap, right? And let's shrink that down a little bit. Let's see what, because then let's see what our object is doing. So let's go on the interval now. Instead of 3 to 6 seconds, let's go on the interval from 3 to 5 seconds. Okay? So d of 5 is going to be 75. 5 squared is 25 times 3 is 75. Okay? Minus 27 all over 5 minus 3. 68, 48. So I get an AROC there in that one of 24 meters per second. Yeah? Still, big gap, right? Okay. Let's kick it down another second. From 3 to 4 seconds. Four squared is 16 times 3 is 48. Yes? Okay. What's our object doing? Between 3 and 6 seconds. It's accelerating, right? Yeah. Because the smaller we're getting, we're shrinking it in, so we're kind of like bringing it backwards, and we're getting smaller numbers. Okay? So that means that it's accelerating if it's going faster over a longer period of time. Okay? Last one. What if I did this? On my interval, 3 seconds to 3 seconds. It would be, wouldn't it? Right? Because it's what the velocity is at 3 seconds, right? Okay? So this would be 27 minus 27 all over 3 minus 3, which would be what? 0 over 0, right? And we can't divide 0 by 0. Okay? So the IROC is just that. Okay? So this is our IROC, which means we need a new method. We can't just drop down our interval until our interval is 0. And because we would be dividing by 0 every single time. And that just can't happen. Okay? So an instantaneous rate of change is how fast that object is going at that moment. Or the rate of change again, I used this one earlier today. Okay, the instantaneous rate of change, your IROC, is your speedometer. Okay, it's how fast you are going that moment. Okay, okay? That's your IROC. Okay, so let's get into it. Given that d of t equals t squared, represents the distance an object is from its starting point in meters after t seconds, find the IROC at 3 seconds. Okay, well, to speed things up a little bit here, okay, this function has a vertex at the origin. So if I plug in 0, I get 0. If I plug in 1 or negative 1, those both square to be positive 1. So it goes through point negative 1, comma 1, 1, comma 1. If I plug in 2 or negative 2, I get positive 4. If I plug in 3 or negative 3, I get positive 9. 4 would be 16. Likewise, negative 4 would be 16. So here is my function. I want to know the IROC that's going on right there. Okay? I want to know the instantaneous rate of change right there. So what we could do is we could find the AROC on a really, really, really small interval. Like from 3 to 3.1. Okay, we could do that. But it still wouldn't be instantaneous because that 0.1 second is still, I mean, it's a blink of an eye. So it's fairly measurable. Okay? So we could shrink that down even further. To 1/100th of a second. Okay? But we could keep doing that, keep doing that, keep doing that. Eventually, we're going to come into using something called a limit. Okay? Now, I don't remember. We're going to use something called limits. Okay? So the interval that we're going to use we're going to go from t to t plus h, and we're going to make h 0, is what we're going to end up doing. That process is called sending h to 0. Okay? So we're going to send h to 0. Because then, if h is 0, now my interval is from t to t. Okay? Okay? How we do that is we're going to use our average rate of change dq, and so we're going to say that this is going to be the limit as h approaches 0. H is going to get closer and closer and closer to 0 until we can send h to 0. And this is going to be of the function f of t plus h minus f of t all over t plus h minus t. I'm going to use the dq on that because I can't send it to 0 quite yet. You'll see why here in a minute. So my IROC function at time t then is the limit as h approaches 0 of f of t plus h minus f of t all divided by h. So I've got to do all of my math first, and then at the end, I can do what is called sending h to 0. Okay. Now, there's going to be some math involved in this. Okay? Historically, it's not the calculus that calculus kids struggle with. It's the algebra that calculus kids struggle with. Okay? So the way that you can get around that is you can write your work down. Try not to do as much in your head. Do more on paper so you can see it and think about it at the same time. Okay? And then you're not getting things confused and befuddled. Okay? So, if I want to find the IROC at t equals 3, which is here on the next page, okay? That's going to be the limit as h approaches 0 of that. Right? Okay. Well, let's figure out what d of 3 plus h is. That means I'm going to put 3 plus h back into my function in place of t. So that's going to be 3 plus h quantity squared. Agree with me on that? That means that this is 3 plus h times 3 plus h, which is 9 plus 6h plus h squared. Agree with me on that? Plus h. I put curly q's on the bottom of my t's. What is d of 3? D of 3? 9. Can I send h to 0 yet? Why not? H is still on the bottom. Yep, so I can't send it to 0 yet because I still have an h in my denominator. Okay? Alright, so I can't send it to 0 yet. So let's keep doing some math. Can I simplify that fraction at all? Okay, what does it simplify to be? Yes? Okay. can I simplify that fraction at all? What can I do? Factor out an h from the top. And then, Alan? Now I can cancel out an h. Yep. Can I send h to 0 now? Yeah, because I don't have that denominator being 0 anymore. Okay? So now I can send h to 0. So this would become 6 plus, if h is 0, then that's 6 plus 0. And what is 6 plus 0? Just 6, right? Okay. So my IROC at t equals 3 is 6. We don't have any units on this function. Or wait, did we? We did, because this was meters per second. This one we did. So my IROC is meters per second, because it was distance the object is away from the starting position. Okay? Find me the AROC at, or on the interval 1 to 4 on the next page. Not that. Function Z. Don't have labels, so we can't go meters. If you put meters per second, that's fine. I get an AROC of 10. Do we agree? Okay. All right. Find me the IROC at t equals 1. I get the IROC at t equals 1 to be 4 meters per second, we'll say. But we don't have to. So we get an IROC of 4. Yes? Okay. I handed out to you the first worksheet A. There'll be a worksheet B, worksheet C, and worksheet D this week. So, okay.
What are they?